All right, so we're going to do one more trend here as a podcast talking about ionization energy, the same way we did atomic radius. So this is going to cover page 4, and we're just going to jump right into it. Remember, we're going to skip the periodic table for now and use that in a moment. So let's write down our definition. What is ionization energy? Well, this is the energy, as it says, to remove or ionize an electron from an atom. That's what ionizing is, creating an ion from an atom. And ionization energy is just the energy that we need to put forth or use in order to make that happen. We could write an equation for this general process, and imagine A is any atom, and we need to use some energy, put some energy into a reaction, into a substance, in order to cause that substance to become positively charged, in order to pull this electron off and have it go off and do something separately from that original atom. Now, this is going to change across our rows and our columns like we've already done with our atomic radius. So in respect to the nuclear charge, as we're moving across a row on the periodic table, because we're getting more and more of those protons, getting a higher nuclear charge in the atom, protons are going to be holding on to the electrons more tightly. The more of them there are, the higher that nuclear charge is. So if they're holding on to the electrons more tightly, it's going to take more and more energy to pull those electrons off of the atom. So that ionization energy is going to increase as we move across a row. As we go down the periodic table, and when we have that shielding effect happen, moving down a group or column, we're adding higher and higher energy level electrons that are farther and farther away from the nucleus, so they don't feel as much of that charge. They're more shielded from that nuclear charge, which means that they're not held as tightly, and that ionization energy is going to decrease as we move down a group or column. So putting these two trends together on that periodic table that you've got up top, if we are increasing as we move from left to right in a row and decreasing as we move down, that means our biggest ionization energies are at the top of our columns. Then these are the arrows you should be drawing on that periodic table at the top of the page. And if we put those together, they are pointing to that top right element, helium. So He, helium, has the greatest ionization energy of all the elements on the periodic table. And as we're working these next few practice problems, the closer to helium we are, the larger our ionization energy will be. So just a couple of quick practice problems, and then we'll finish off that page. Not really much more to write. So we're going to be looking for the highest ionization energy, which does mean closest to helium. So I'm highlighting each of these pairs. Which one is closest to helium? Well, that's our oxygen. So oxygen has a higher ionization energy than nitrogen. And then if we look at these three elements, which one is closest to helium? Well, that's going to be that neon. So that is our higher ionization energy out of those three. I'd like to see what you think out of these other three elements, nitrogen, arsenic, and fluorine. Which one has the highest ionization energy, do you think? Make that one last circle, and then we're pretty much done. Just want to kind of talk about this general idea of ionization again. We can pull off individual electrons here, which is what this ionization energy is kind of measuring, but understand that there are actual multiple ionization energies for an atom. So sometimes this ionization energy is called the first ionization energy, because we can continue to take a second electron off, a third electron, a fourth electron, and generally we need more and more energy to remove those electrons. But what this is specifically mentioning here at the bottom of your page 4 is that once we get to that noble gas configuration that all of the elements want, once they get those 8 valence electrons by gaining or losing, then that ionization energy becomes huge. You can see that here with magnesium. When it loses its first electron, its first ionization energy is 738. When it loses its second electron, that goes up. Its second ionization energy is 1,450. It's doubled. But then if we try and take another electron off, this is where we become core electrons. Magnesium wants to be a +2. If we try and make it a +3 charge, then all of a sudden, this hasn't just doubled. This is like quadrupled or more in the amount of energy needed to remove that electron. So it's really, really hard to get magnesium +3 and magnesium +4. You have to put a lot of energy in order to make it happen. It can technically happen, but that ionization energy is a little bit prohibitive. So that's what we're talking about here. But in general, especially for this unit, we're just focused on that first ionization energy, just the energy to pull off that one last outermost electron. And that's it. Hopefully this was pretty painless. Next class, we're going to be practicing our atomic radius and ionization energy trends together. So make sure you got these notes. Come in with any questions that you got.